你 n 加一嘛，你 n 加一的那一步讲变成 n 加一，你是不是刷？还是你换的？对啊，你就刷对。然后你还要什么？你还要什么？
算是 transposition matrix 这个东西是
什么？
事实还是要 prove？
这样的话，你要去找一个 matrix 帮你刷 row 的是长这样。
你双漏那个应该去把它讲，其实就是两个不一样，
什么意思？
就两个泰国那个交换的。
没有。嗯。啊，对，然后。
这样子。
嗯。Okay, I think we should follow the times. Okay, let's start. I wonder if you guys see this advertisement before. This concert. Huh? The concert name is plus minus equals to divide multiplication. Division multiplication. It's a mathematics tool. Action by action. Oh. So yes, this thing is correct. Huh? I don't know. There's a what? There's a reason he put this sign on for his album. 5 albums. Yeah. So so I didn't say what is two elements to be conjugate to each other, but you need it for your assignment, right? So Dongjie asked me about it. It's really the idea of similar matrices. Okay, so it says that. So if you can, you look at this last line here. So this last line here. And A is conjugate of B if there exists another element in G in your group such that A equals to GBG inverse. Okay, so this is what it means by two elements to be conjugate to each other. Okay. Yeah. So note that it is conjugate in G in different G, so you need to find G from different group. Okay, depend on the question. If say that A and B are conjugate in G, then you need to find element in G. If the question say find show that A and B are conjugate in G prime, then you need to find element in G prime so that they conjugate. Okay. Yeah. Any question on different part of the lecture? So please update look at my updated notes. Okay. Check the date I upload the notes and then try and update the notes. And so my note is important because when I do tests, right? So I will typically test on the things that I focus on. Okay. But test book is also important. So you need to use both to read together. Okay. Yeah. In my notes, sometimes I point out what is important. And then sometimes the textbook has different presentation of the proof or different idea. Then you can also read. Okay. Read both. But anything about my lecture notes, right? You should come back to me and then ask me. Okay. Any question? Question? No. Okay, understand. You want to hear a story or not? One story, morning story, story time. Okay, I tell a story when while we get ready, and then most of you haven't come yet. So, my brother went to an interview by Shell last weekend. By Shell, do you know Shell? An oil company in Malaysia, Shell. So he said he was terrified by the interview. So what they do in the interview was, he asked my brother to read a case study for about 20 minutes or 30 minutes, okay? And then start asking him, okay? So for example, the question they ask is, why we can invest here, okay? How to invest here? And then tell me the plan, okay? So my brother did it, yes, did it. But it's why he was terrified. And then he said he want to leave the room, okay? He said, the interviewer keep asking him the same thing. He said, I already mentioned to him or her, okay, but he still keep asking the same thing. And then he said that he don't know how to answer the interviewer. And then he feel like he want to leave the room. Okay. So this is the real work life you're gonna meet. Okay, maybe depend on the level of the company you go, right? Okay, but if you want to go big or go to a better company, get a better salary, then these are the skills you need. You need to be able to explain, again, in different way, from different view, right? So there's another point. You say that the interviewer like to input random things, okay? And they input random things and they ask you for opinion. Okay. So you see, what is this called in Chinese? You know? So in Chinese it's called 不按牌理出牌. 不按常理出牌. Okay. Right. So you need to prepare for these challenges. Okay. Otherwise, you are just simply a worker. Okay. So you need to be prepared. And the very good place for you to prepare is here. Because why? Even you get bad result, you still here. If you get bad result in interview, what happens? No jobs. No jobs equal to no money. No money equals to what, Vincent? No money, who gonna feed you? Huh? Your parents. Your wife. Okay, good wife. Okay, right. So here is the place to develop your talent, develop your abilities. Okay. Yeah. So let's start. So let's repeat what we have did for the past few lectures. Okay. So we still have this picture of homomorphism. Okay, group homomorphism I hope that the definition of group homomorphism is already instilled inside your mind. Okay, you never forget already. Multiplicative property, okay, satisfied by a map. And within this homomorphism here, there's an interesting object we can study. Is the kernel. Okay, kernel. What are kernel? Kernel are the things that get sent to zero or identity, okay, in the codomain. Okay, so with this kernel, right, what things you can build? Kernel, in particular, kernel is a subgroup. Okay, kernel is a subgroup. Okay, so kernel is a subgroup. What can you do? You can take the coset. Okay, you can take the coset. Left coset, for example. Okay, we got AK, BK, CK. Okay, and then under the map, what happened to these sets? For example, kernel will get sent to the identity. Okay, and then AK will get sent to phi A. Okay, phi A. Right. Okay, and then BK will get sent to DB. Hey, by the way, how do you read these? Phi or phi? Phi. Phi and phi actually both can. I go search already. So phi is English. Phi is modern Greek. Yeah, up to you. Phi or phi? I prefer phi. Huh? PHI. PHI? What do you mean? Phi. Oh. Yes. Okay. Yeah. And CK will go to C. Okay. Okay. So, so the corollary following from last week, okay, we want to show that the left coset, okay. So from the picture here, right, can you guess anything or not? Okay. So what's the left coset? What's the number of left coset of kernel phi? Okay. In other words, what's the index of kernel phi? Can you guess from this picture here? Equals to what? Equals to what number? Can you guess from this picture here? So what's the index of kernel phi in this picture here? You know? You know what's the definition of index of a subgroup? What's the definition of the index of a subgroup? Number of left coset. Okay, so how many number of left coset here? 4. Okay, so this 4 here equals to which 4? Which other 4 in the picture? Can you guess? There's not many picture and not many number in this picture. Can you see another 4 in this picture or not? Don't just look for this 4. It is not 4 anymore. It's a object. 4 objects. Okay. Which 4 objects you see? Other 4 objects you see in the picture? Sorry? The element in G prime. Okay. So there's 4 elements here. So what are these elements? Can you categorize these elements or not? These are what? Left coset. I mean, it is a left coset, but can be simpler. The answer can be simpler. Sorry? Image. Good. These are the image. Okay? Image of phi. Okay, so these are the image of phi because you write it as phi of something. Okay, so these are the image of C. So we're going to prove that the number of left coset is actually equals to the cardinality of the image of F phi. Okay, you know what's the image of phi? Everything that mapped by phi. Okay, phi of something, phi of something, phi of something, phi of something. Okay, so these are the image of phi. Okay, you are the image of phi because you can reach by phi, taking phi. Okay, so these are the image of phi. So how to prove this? Okay, so you have a subgroup and a group. Okay, remember what's the Lagrange theorem tells you? Lagrange theorem or counting formula? Okay. Order of the element can divide order of the group. That one is one of the corollary. Okay, when you look at the cyclic subgroup. Okay, but what's the general statement here? Okay, so what's the general statement here? So let me put here. So let H be a subgroup of G, then the order of the group divides order of groups. Okay, but what's the multiple? What's the multiple here? Index of H. Good. Okay, so this is the Lagrange theorem and counting formula. So if we apply on this case here, what's the subgroup we are interested? We have the G. Where will H here? Only this section. Okay, so I should need phi G to G prime. Okay, so in this case here, what's the subgroup we are interested in? Yeah, H is what? Yes. Okay, so take H to be the kernel of phi. What do you get from this theorem? Then the order of group is divided by the cardinality of the kernel with the index of kernel. Okay. So how should we prove here? So we want to show two sets with the same cardinality, right? Last time, what do? We need to form a bijection. Okay, we need to form a bijection. If you have bijection on set, then their cardinality is the same. Okay, this is applied for finite group, finite set. Okay, finite set. Wait. Okay. So let's define a map. So define a map from the left coset to the prime. And then by sending a coset to its image. So is this phi? Okay. So let's define another. Let's use another notation so that we don't confuse ourselves. So let's define F. Okay. So is this F a homomorphism or not? You can try and think about it, whether it's this homomorphism, but later we will see a group structure on the left coset. Okay, but it's not important for now because we just want bijective. Okay, bijective is important because we want to show that cardinality is the same. Okay, so the claim here, so I mean you can think about it. So think about it. If this is homomorphism. Okay. So claim we just need to show that F is bijective on X image. Okay. So first we can show that whether it is injective or not. Okay. So is F injective? So how to show injective? Okay. Suppose F A equals to FB. Okay. I want to show that AK equals to AK. Okay. So think a minute how we're gonna show this. Okay, yeah. Think a minute. Here, I think I put something wrong here. There should be F8. Okay, so image equals, meaning that you have to start from the same place. This is injectivity. Okay. So if the image is the same, you must show that the pre-image are also equal. Okay. So you only have one, really, you have only one assumption here, right? Okay, so you need to start with this assumption. Okay, so what does this assumption give you? What is f of AK? Is phi of A, okay, equal phi of B. Okay. What does this mean? This means what? This means what? These are groups element, right? Okay, what can you do? You can take inverse. Okay, you can play around with it. Take inverse. Okay. But phi is a what? Phi is a map from group to group. In particular, it is a homomorphism. Okay, recall what is the properties of group homomorphism. Okay, phi A equals phi A times phi. You can bring the inverse inside. Okay, and what can you do? You can combine, right? Combine and split, split and combine. Okay, this is the group homomorphism property. Become AB inverse. So what does this mean? This means that AB inverse is in the kernel. Remember last time we have these equivalence proposition. The following are equivalence. Remember? So let's recall that what we proved last time. Yeah, remember this theorem here. Okay, so if you get any of these right, okay, then they are all equivalents. Okay? You can go from one line to the other lines. Okay, just now we got what? We got this line. That's 2. Okay, so but what do we want? We want to show that their coset is the same. Okay, so we can go from 2 to 4. Okay. Really, if you really remember this proposition here, we can just start from 1 to 4 because 1 is exactly what's our map. Okay, phi x equals to phi y. Okay, yeah. Yeah, this is a good exercise you have to master, whether you know how to apply definitions or not. Okay, no construction involved, just need definitions, set definitions, group definitions. Okay, yeah, so by proposition, by position AK equals to BK. So the left set coincide. Okay. So it's injective, then on its image it must be surjective. Also it is bijective. Okay. Not that we don't need to cover the whole G prime, okay? We don't need to cover. Depend on what's the image of my phi. Okay. Yeah. We don't need to cover the whole G prime every time. Okay, depend on what my phi is. If my phi is surjective, then image of phi is equal to G prime. Okay. But this F here is always surjective on the image. Okay. Can understand what I say? Yeah. Okay. So I will say that F is automatically surject. F automatically surjects on its image. Okay. Because image is what? Phi of something. Okay. So this means that everything in the image must have a pre-image. And this is the definition of surjectivity. Okay. Okay, let's continue. So the corollary here is let phi be a homomorphism of finite groups. Then the following holds. Okay. The order of the group is just kernel of phi multiplied by image of phi. Okay. And then from here you can see that the kernel of phi divides the order of the group. And then the image of phi divides the order of the group. Okay. You can see clearly from the first expression here. Okay. But it also divides the order of G prime. Okay. Any idea why? Why divide the order of the G prime? Yuanjia, do you know why? Where does the image of phi live? G or G prime? Huh? Where does the image of phi live? G or G prime? G prime, right? Okay. So how, in what circumstances you will divide the order of your group if you are a subset? Okay, so my question is, when is the order of H divide order of group? When is the order of H divide the order of group? When H is a subset of G. What happened? When this is a subgroup, right? So if you are a subgroup, then you will divide the order of your group. Okay. So is H a subgroup or not? Is image of phi a subgroup or not? Yes. Okay. Image of a homomorphism is a subgroup. Okay. Then pre-image of a subgroup is a subgroup. Okay. I have to remember this fact. Okay. Yeah. And then we prove it before. So because image of phi is a subgroup of G prime. Okay. So the order, so you must remember clearly, the order of a subgroup divide the order of the group. Okay. And one important example of subgroup you need to know, few examples. So one is cyclic group, okay, and then the other one is the kernel of any homomorphism. Okay. Okay, so let's look at one example here. So this sign, remember the sign homomorphism we talked about last time? Okay. So let's say we want to find what's the kernel of this map. Okay, what's the kernel of this map? So meaning what are the elements get sent to +1? Good. So these are all the alternative group. Okay. So the kernel of sign is equals to the alternating group. Why? Because these are precisely those can be written as the product of even permutation. So I ask you, what's the cardinality of AN? Okay, what's the cardinality of AN? How do you count AN? Okay, how to count AN? How to count AN? How do you get that? How do you get that? Is it? Is it that obvious? Don't think it's that obvious. How do you know that even and odd split into half of Sn? Sure, we can use the Lagrange. Or you can try and compute by hand what happened. Okay, what is A2? What is A3? What is A4? What is A5? Okay. But you can see that these numbers grow relatively fast. Okay, faster and faster. Okay, so how fast it grows? So we can use technology here, right? So what's the image of a sign is? Okay, just now we proved that the image of sign is equals to what? Equals to the number of left coset. Okay, but what? But what's the image? What is the cardinality of my image? Here. How many image here? 2, right? So you see, Sn, the cardinality of Sn is really big. It's like n factorial, right? But the image is like always 2. Okay? Yeah. So what do we have here? So what's our formula for our Sn? Okay. Our Sn is equals to the kernel of sign multiplied by the image of sign. Okay. So I think I have some order issue here. So the left coset is equals to the image of sign. Image of sign is equals to 2. So we know that the order of Sn is n factorial. Kernel of sign n, this is what we want to find. And then image of sign n, we know that this is 2. So we can deduce that the cardinality of the kernel of sign function is n factorial over 2, which means the order of an is n factorial over 2. Okay? Or really care about the order, we should put like this. Yeah. So it grows like 1 n factorial over 2. Okay, an. All the even permutation. Okay. Yeah, any question? Please stop me if you have any question. Feel free to stop me. Okay, another tips I want to give you. So if you say that I don't understand what you say, I cannot ask any question. So you ask me to repeat. Just ask me to repeat. Okay, ask me to repeat. Okay. You don't need to ask question. Ask me to repeat. Okay. See if I can explain in different way or not. Okay, just ask me to repeat. Okay. Okay. Okay, next. Multiplicative properties of index. So you see, in algebra, we like this kind of properties, multiplicative properties, additive properties, and so on, because we care about the structure. Do they have new structure or not? Okay, if I define a new object, does the object has new structure? Okay, and then whether this new structure can tell any things about the old structure or not? Okay, yeah, this is typically what we do in algebra. Okay, so for example, okay, let's have a subgroup of G. Okay, so if I write it this way, it means that G contains the subgroup H contain a subgroup K. Okay, so these are subgroup of G. Subgroup G. Okay, then okay, so this is a multiplicative property of index. Can you guess what's the statement we want to get here? So must be involving index. Okay, so how is it multiplicative? Multiplicative means what? FAB equals to FA times FB. So something need to combine, something need to split. Okay, and then you have index. So how you put these things together? Guess the statement first. Okay, by guessing the right statement, you are almost 25%. Okay, to proving this statement here, proposition here. Okay, so anyone want to guess what's the equation we have about index? So index is a number, right? Okay, so we have some equalities on the number. Anyone want to guess? What's the statement here? What can be split? What can be multiplied? What can form an index? This, but there's no index involved here, right? For these, we will see later on product groups. Okay, but it's not this here. So we need index. So out of these three subgroup, right? What kind of index you can form? What kind of index you can form? No, I mean what kind of index you can form? Index of H, index of K, right? So index of H, there's only really one type, all right? Because H is a subgroup of G. You cannot write K, index of H in K, cannot, because K is smaller. Okay, you can form GH. How about index of K? How many index of K you can form? Two types, right? Because there are G contain K, there are H contain K. Okay, so you can form G, K, you can form H, K. Okay, so if I want to have some multiplicative property, how should I arrange this number? Any idea or not? Want to guess? How I arrange these three numbers? GK equals to GH times H. Okay. See, this is somehow similar to like chain rule or chain rule, right? Chain rule is what? Okay, let's cue some calculus out. dy dx or dy dt equals to dy dx times dx dt. Okay. You see like some structure involved here. Okay, so this is a general phenomenon you will see across mathematics. Okay, these are multiplicative structure. Okay, so Yeah, so this is the statement we want to prove. So let us get rid of all these first. So I let you spend about 1 minute to think about it. How you're gonna prove this? Talk with your friends if you like. Okay, how are we gonna prove this? Think about, start from the definition, okay? Start from the definition. What's the index? What's the idea of index? Okay. What does left coset do? Okay, I won't give you the full proof, but I'll draw some intuition to you. So we have G, right? Okay. On the left hand side, what does it do? So you can partition, okay, partition your G using the left coset of K. Okay, so let's partition it. Okay, for example, like this. So K, AK, BK, CK, DK, EK, FK, GK, something like that, right? Okay. But on the right hand side, what do you have? My right hand side. Right hand side is your right hand side as well. Okay, good. So, what do you have? Okay. First, what do? You have the same group starting first. Okay. What do? You first split your G using H first. You split your G using H first. So maybe let's change the color. So you split your G using H first. Okay, H, H, 3H, 4H, for example. Okay. Right or not? Make sense? Does it make sense? Okay, so the idea I use here, maybe I need to recall for you. So the slogan here is left coset partition the group. Okay, left coset partition the group. This is what we prove. Okay, if you forgot the proof, you need to take my word now. Okay, left coset partition the group. Okay. Go back and revise. Okay, so but you know that left coset of K also partition the group H. Okay, so meaning in every group here, they get partitioned by K. Okay, so okay, let's take it slowly first, right? Let's take it slowly. Let's take this guy. Okay. So let's say I can partition my H into AK, BK, okay, A prime K, B prime K, C prime K, and K. Okay, what does it imply for the rest? These are coset. These are not group anymore. Okay, but how far is it different from a group? It is just multiplied by one element here. Okay. So you can also multiply this element to all these coset here, and then they will help split your coset. Okay, using K. Do you get what I mean? So for example, I can get 2A prime K, 2K 2b prime k, 2c prime k, like this. Does it make sense? What's the difference between h and 2h? You multiply 2 to every one, right? To everything in the elements, okay? If I can split h partition by this coset, okay, I can also multiply 2 to this coset. Make sense? Does it make sense? Okay. And then we can do the same thing, right? For 4h, what do? You can split into 4a prime k, 4b prime k, 4k, 4c prime k. Okay. And then the claim is these two ways of splitting is the same. Okay, these two ways of splitting is the same. Why are they the same? Because what? Because what you do on the right hand side here, you are actually forming a left coset of k inside G. Okay, so they should really get the same number here. Okay, because what you are constructing on the right hand side here is really all the left coset of k in G. Right? You see, we start from k and then we build this left coset here. Okay, so by definition, these are the number of left coset in G of k. Okay, of k in G. Make sense or not? Any question? Question? Simple, yeah, simple. Sorry, G in what? G index H is 4. Yeah, in this case it's 4. It's also 4. G index H. Yeah. Huh? Yeah, right. I mean, how to say? Okay. Okay. If you like, right? I can add more for you, but it doesn't change my argument. The key point here is how I construct these concept. Okay. Okay, I know where's your point. I mean, but that's really not the point I'm focusing about. But I understand why you are so particular about these things. So one thing, okay, you can keep that in your mind. But one thing I want you to know from my argument just now is how we construct the left coset of K in G. Okay, this is the main thing I want you to get. Okay, so the left side is whatever GK give you. I don't know, whatever. That's why I simply put a number here, whatever it is. But on the right hand side here is a particular way to get the number of left coset K in G. Okay, how to get it? First, you split your G into partition by H first. And then you split your H into partition by K. And then if you can add up all the number of left coset built up by K, okay? So the claim is what you do here are all the left coset in K. Okay, this is a claim you need to check. Okay, actually the way you build all these left coset is really the left coset of K in G. Okay, and then by definition, they have to be the same. Okay, I don't care how you compute it. But by definition, they have to be the same. Otherwise, something is wrong. Okay, something in the argument is wrong. Okay, Okay or not? Yeah. So the technical part in this proof is to see that the way you build this left coset are really different coset in G. Okay, left coset of K in G. Okay, it's not the case that like F B prime K will be equal to some, for example, B prime K. No, they are not. They are pairwise different. Okay, so the argument you need to check is this one. Okay, that's the technical part. If they are all different, then by definition these are all the number of left coset. So from both way you should get the same number because that's the definition of left coset. Okay, yeah. I will write out the full proof, and the full proof is also in the textbook. Okay, but the idea is like this. Okay, so you cut your G using H first, and then you cut H using K. Okay, and then you add up all the way you can cut using K. Then this is really the all the way you use left coset of K. Okay. Yeah. Question. Sorry. Cardinality. What do you mean? Oh, okay. So you okay, in that case, unless you make K a kernel, right? Is it? Wait. So why? Okay. So you are thinking about making this cardinality into this. Okay. So why is this true? How is this true? So if this is true, this means that cardinal of K equals to cardinal of G. Okay. So is this true or not? Is this true? Can we go backward? So why is this true? Because K is the subgroup of G. Right. By counting formula, this is true. Okay. Okay, good. So Ying says, how about we try this? Okay. And if we have these, right, so we can really replace G and K with other things, right? So for example, we can replace what is HK and what is GH, right? So what is these numbers? So these are H, K, and this is G over H. Okay. So to prove that GK equals to HK, sorry, so we have a GH first and GK. Okay, so to prove that this is true, this is just amount proving that the cardinal of G divided cardinal of K equals to cardinality of G divided cardinality of H times cardinality of H divided cardinality. Okay. Okay. But the last line is always true, so we can go back. Yeah. Yeah, you can prove it in this way. Yeah, you can prove it in this way. But you see, there are two proofs here, right? What's the difference between these two proofs? So this proof, this calculation here, these are just number calculation. So this obscure what's happening inside these multiplicative property. Okay. So the first proof we describe here really tells you how to cut the set. Okay. Yeah, so that's why I'm keep emphasizing these ideas to you. So like in calculus 2, right? I don't want you to just count. I want you to know what are you counting. Okay. So the first proof tells you what are you counting here. Of course, you can use the second proof to prove it, but what does it tell you about the coset? What are the coset are doing? Right? What are the coset are doing? Okay, why two ways of cutting get the same number? Why? You have an answer. Okay, if you use the second proof. So the first way, the proof to you how you cut your group using coset. Okay, two different way of cutting it. I mean, yeah. Yeah. Do you get the same number of index or not? Okay. Yeah, this is what I really want you to appreciate from learning pure maths. Okay. Any question? Any question? Yeah. So you can put two proof here. So one is just calculating number, the other tells you how to cut the coset. Okay, let's finish one more coset and then we will take a break, okay? So last time I asked you to think about what's the definition of right coset, right? Okay. So what should a right coset be? So the right coset of a subgroup H of a group G H times A, okay, for all the A's in your group G. Instead of multiply on the left, you multiply on the right. Okay, so let me show you one example. Okay, let me illustrate one example for you to see what happens with these left and right coset here. So for example, let's take a group generated by 1, 2. Okay, so this is a cyclic subgroup generated by 1, 2. And then this is a subgroup in S3. I want to take it in S3. Okay. So in particular, this is a subgroup. I can form a left coset and right coset. Okay. So let's write down here. So inside my group, there are really only have two elements, E and 1, 2. Okay, because 1, 2 is order 2. Order of the elements is equal to the order of the group if the order of the element is a prime. Okay. Okay, so what can we do? Okay, let's form left coset first. Okay, AH. Okay, let's form AH. Okay, what A you want to pick? Okay, let you do experiment now. What A you want to pick? Means you what you want to pick? 3, 1. So meaning 1, 3. Okay, so let's do 1, 3. What do you get? You get 1, 3 times 1, 3, 1, 2. What is 1, 3 times 1, 2? Thing. 1, 3 times 1, 2 is 2, 3. 1 to 2. 1 to 2, right? And then 2 to 1 to 3. 3 to 1. Right? 1 to 3. Correct? 1. Okay, so first you encounter the rightmost transposition first. So 1 will go to 2. Okay, 2 goes to nowhere, so stop at 2. Then 2 to 1, 1 to 3. Again, 3 go nowhere, so 1 to 3. And then 3 to 1, so cycle back. Okay, 1, 2, 3. Okay, hopefully you have mastered this computation. If not, do it again. Okay. Yeah. Any question on the multiplication on this thing? Transposition. Okay, by now you should be quite good, fluent in multiplying these. Okay, okay, okay. What other A you can try? Grace, what A do you want to pick? What other element in S3? 2, 3. Sure. Let's try 2, 3. Okay, what happens if I take 2, 3 multiply to the H? Okay. So first will become 2, 3. The second will become 2, 3 times 1, 2. Okay, so what's this 2, 3 times 1, 2? And 1, 2 is really what? 1 to 2, 2 to 3, okay. 3 to 2, okay. 2 to 1. So 1 to 2, okay. 1 to 2, but the next one will send 2 to 3. Okay, so we stop at 3. But where does 3 go? 3 goes to 2. Okay, but so we stop at 2. And then 2 goes to where? 2 goes back to 1. Yeah. Yeah. Okay. Any other? You can pick any other A you can pick or not? Yanker, pick another A. What other A you can pick? How many elements in S3? How many elements are in S3? 6. Right. So far, how many of them we have tried? We have tried 3 of them. One is identity, one is 1, 3, one is 2, 3. Okay. What other elements you can pick? Hey, wait, Yanker, you are Yanker. Yanker. 1, 2, 3. Okay, so you believe your friend. 1, 2, 3. Okay, let's try 1, 2, 3. What happened? So you get 1, 2, 3 times Z. You get 1, 2, 3. 1, 2, 3 times 1, 2 is what? Right, so 1, 2, 3 times 1, 2 is what? 1, 3. 1, 3. Okay, let's check. So 1 go to 2, 2 go to 3. Okay, so we stop at 3. But 3 go back to 1. Okay, good. So 1, 3. So did you realize anything or not? Realize anything? Have we seen this set before? What is this set? Have you seen this set before? 1, 2, 3, and 1, 3. Where is it? This is really what? Which concept? Have you seen this before? Compare. Have you seen this set before? Xuan have you seen this set before? Which one? Yes, good. So 1, 3, H. Okay, so you see, you take 1, 2, 3 times H, and you take 1, 3 times H, they are really the same concept. Okay, so that's the faster way to compute this guy, right? Okay, if you can split, why I asked you to split into transposition, okay? Because you can have a faster way to compute the cycle. You don't need to go one by one and count, right? So you just make the cancellation here. You get 1, 3. Okay, right. Imagine you have some longer 100 cycle. How are you going to count one by one? Right. Okay. So if you split into transposition, then you just check whether transposition they can cancel on. All right. So similarly, maybe we just skip the computation. You can try 1, 3, 2. Okay, and then you will check that. Actually, see who have 1, 3, 2. The coset 2, 3 times H. That should equal. Okay, you can go and compute it. Okay, try check yourself, convince yourself. Okay, and there's one more to go, right? You can multiply by 1, 2 as well. But you know that H is a cyclic subgroup. So if you multiply 1, 2 into your cyclic subgroup, you really just get back your H as well. So what do we get here? What's the number of coset here? What's the number of coset H? Coset of H. What's the index? In other words, what's the index of H in S3? Equals to how many different coset here? And here how many? 3. Okay, because these are H, 1, 3 H, and 2, 3 H. Okay. Does this match up with our computation just now? The number of coset equals to times the order of the subgroup equals to order of the group. 3 times, what is the order of our subgroup? E and 1, 2, S2. What is the order of S3? 3 factorial, which is 6. Okay? See, we break 3 factorial into this meaningful number here. Okay, we have a subgroup, and then 3, where does it come from? Come from the. Okay, so this split by 6. So my 6 becomes some meaningful number here. Okay, it's not just individual element. Right? I split the 6 into some structure of group. Okay. So first, how you count 6? Because you count by element. But now I tell you how you get the 6. You get the 6 by considering a subgroup. Okay. Yeah. So this is the thing we need to always think about in algebra. What's the thing you are calculating? Okay. Yeah. Why we can split 6 into 3 and 2? And are there any ways to split 6 or not? Okay. Yeah. So this is the thing we need to consider. So similarly, so just now I introduced right coset, right? Okay. So what happens to right coset here? Okay. So for example, we pick some representative, right? So let's see if left coset and right coset equal or not. Okay. So meaning, how about we consider H13 and H23. Okay. Let's see if they are the same. Okay, let's see if they are the same. I mean, we want to compare them. Okay. Does it matter? Does it really matter if we change the position or not? Is this a new thing we discover or not? Okay. So let's start with the same H. So what is H13? So we quickly compute this. This is 1, 3, and 1, 2 times 1, 3. You should get the other one. You should get 1, 3, 2. And what is H times 2, 3? So it's 2, 3 plus 1, 2 times 2, 3. What is 1, 2 times 2, 3? It's really 1, 2, 3. Okay. So let's compare them. Are there any similarity? Are there any differences? Okay. So you can see that if I swap the representative, I mean, if we change the way we multiply the representative, you might get different sets. Okay, you might get different sets. So in general, what? So in general, left and right coset are not equal. Okay, in general, left and right coset are not equal. But if your H is normal, then they're equal. Okay, in the next hour we'll prove this. But if H is normal, then AH equals to HH. Okay, if when H is normal. Later we'll prove this. Remember last time we comment about this normal property, right? So normal is almost close to a billion. G inverse equal to some other element. We don't know. For example, G inverse equals to B inside your subgroup. Okay, almost close to a billion. But it shows a billions on the coset. AH equals to HA. Okay, it shows a billion on coset. It doesn't show a billion on elements, okay, on the nodes, but on the level of coset is a billion, okay. Some abelianness. Okay, and another remark I want to make here is try and prove this, okay. The number of left coset of F is the same as the number of right coset of H. Okay, try and prove this. Again, let me know how you try, how you go. Okay, and then we can discuss in class if need. And I also heard that some of you have done the tutorial question, right? Other than Jimpo. So if you have done it and your solution is different from Jimpo, right? I welcome you to send to me. I welcome you to send to me, and then so that I can we can share together. Okay. So if your solution is different from Jingbo, or sometimes right, Jingbo is very tired already. He don't want to complete the argument. So if you can help him to complete the argument, you also send it to me. Okay. So if can, right? How about like this? Any one of you volunteer. Okay. You can type out the solution in LaTeX, and then we can post it. This is actually a project, because these books is always used by algebra classes, but there's no solution one, no solution manual. Okay, all the solution online are done by people. So if can, we can do a document, typeset your solution. Okay, write it good, perfect, and then we can share it online. And then this is credit to you. Okay, credit to you. And anyone who did it, or credit to the class, anyone who have tried the tutorial. Okay, if volunteer. Okay, do it voluntarily. Okay, so if you are free, if you have the challenge, right? By typing out the solution, you also will learn. Okay, you also will learn. Okay or not? Understand what I say? Understand what I say? Yeah. Okay. Yeah. Let me know if you are interested. Then we can work it out. Okay. So let's take a break until 10:21. I will resume 10:21. This one, product set. This one. Product set. Okay. Okay, in the meantime, let me take attendance. Venus not here. Le Tian, okay. Hui Zhe, yeah. Sang Er, yeah. Yan Ke, De Rui. Yan Ke, you okay with your assignment or not? Yan Ke, okay. Please submit on time. Otherwise, I scared you don't have enough mark. Raylan, 之余，金星，孙林，海人，音波，白英，皮兄，you okay or not with the course content? Huh? Too busy, sleep. Any problem? Just come to my office or yeah, they are like visiting quite often. Wednesday, Friday, I'll be around. Okay, yeah. Otherwise, more and more accumulated get harder. Raylan also, Raylan. Yeah, can come with him. Yeah, alone is a bit harder. Together, then will be there will be motivation. Okay. 英奇，yeah. 何怡，雪妍，嘉业，离开，袁家，文硕，一定，玉维，燕博，yeah. 叶，yeah. 林晶，林晶诶，林晶 not here. 董洁， Jay, you okay with the proof that you asked me? Okay. 英语、友情、真诚、真诚。OK。说您。Yeah. 一。Yeah. 天。首先。莹莹。Grace。Sayed。嘉文。明秀。Hey, 明秀啊？Haven't seen you for a week, Hi. Make sure you wake up, Hey, Why Ying already wake up, why you cannot wake up? Huh? What? Cannot Why Ying can wake up, All people wake up early one. 3, 4 already wake up already. Yeah, so control. Why Ying can make it, you also can make it. Okay. Because you used to be a problem kid. But now okay already. Okay. Yes. Now Ming still got problem now. Go to my Michelle. Okay, you got other math question, you can come to me. Because it's I ask you to take on. You can come to me if you have a problem. Ryan, Ellie, Shimei. Okay. Ziyan. Yep. Ellie. I heard you always only go back and study. You don't, I mean, huh? Oh, okay. How about the other class? Same. But like these are less efficient, right? Waste time or in class. Huh? Still listen. Okay, I'll try I mean, adjust yourself. Infinite 的话就没有什么意义啊，连个东西对称不是什么？你说什么？
就看那个，
你要什么？
就是他那个
number 那个 index
cosine
cosine 啊 number cosine 啊
cosine 那个，如果这个 t 是infinity，
然后
那个就是那个我说的，看不到的要 cosine，
对，
就是必须是 infinity，必须是，
或者你要问什么？
就是我说的那个必须 infinity，这个东西就是 index，
对，就 infinity，
必须 infinity，
对，什么呀？
为什么
definition of 这个是 number of constant，所以你对什么问题？我不知道你什么问题啊。
就是
如果 infinite，如果把它切成infinite pieces 是吗？把它切成 infinite pieces，还是这样？它的 number 就是 infinite by convention。有什么问题？
你们这种 infinity，它光addition addition 的时候才是那个考虑 infinity，就是你的 multiply，它是不考虑 infinity，就是可以产生你可以产生一个 final，
可以啊，它可以一个是 final，一个 infinite。对， infinity 可以等于 infinity 乘 finite 可以。
就我意思是什么？就是它一个 infinity 的东西，
对，
可以被另外的另外的成一个那个 finite。
可以啊，可以啊，
对啊，
可以啊，比如说那个，比如说 z 啊，
呀，它这个东西不就可以？
可以，可以。
对啊。
然后呢，什么问题？
那是一个不就可以是 finite 东西吗？
就是有一个例子是这样，我跟你讲，一个例子是这个嘛，我可以 z 用 trivial group 嘛，这个东西是 infinity 嘛，但是呢，如果把它切成这个的话，这个就两个嘛，odd or even，但是呢，这一个对于这个又是 even 的了，对的。infinity 等于2乘 infinity，是你要加吗？我不是很懂你要讲什么。这个可以是 infinity，这个是你要的，但是我们不就没有
这可以是那个 finite，
对啊，finite，
那可以是 finite。
这个东西可不可以 finite？
对啊，
可以啊，可以啊，这就是 finite。
就是既是 infinite，就是 infinite，part of the，但是这个不是。
那种再来一次，
就如果既是 infinite，
怎么可以又是 infinity 又是 finite？没有可能的。
就是可以把那个 infinite 东西拆成一个 finite 东西。
可以啊，可以啊，可以啊。
然后那这样不也可以吗？就把它拆成一个。
你说谁是 infinite？你是说 order of G 是 infinite 还是谁？
对，到了 G。
哦，可以啊，可以啊，可以啊，可以啊，可以啊，没问题啊。
对啊，可以就可以是。
可以，来这个 G 是 infinite，这个也是 infinite，那它们是 finite。可以，没问题。呀，但是我只是说，如果这个东西是 infinite 的话，没有什么好吵的，infinity 等于 infinity，不有趣啦，可以啦，就如果 finite 的话，我们就可以这样去。
这个地方，它这个东西，如果是如果这个 h，如果这个 h 是这个 k 的 subgroup，那么它的那个 index 必须是一个 integral，
放在这里哈
，integer，
对，
必须是 integer。
对，因为我们 formal closure 是一个一个算的嘛，没有减的，也没有 half。OK， hello testing。Okay, so Lee had asked a question, right? This proposition. Can group be infinite or not? Can. Group can be infinite. But what I say is, if the index of this subgroup is infinity, then there's nothing much you can do. Infinity equals to infinity times something. Right? So there's nothing much to show here. So the interesting part of this proposition is, if when all the index are finite, what happens? Why are they equal? Okay, why are they equal? Okay. Like for example, I can give you an example of an infinity group. Okay, and then this equation hold. Okay, so for example, take the trivial subgroup in your Z. Okay, take the trivial subgroup in your Z. So what's the coset of your trivial subgroup in your Z? All the numbers 1, 2, 3, 4, 5, 6, 7, everything. Okay, so the index of the trivial subgroup is infinity. But you can split your Z into even and odd. Okay, even and odd integer. So for example, 2Z form a subgroup inside of Z. Okay, and then what's the coset formed by this subgroup here? Is really the odd integer and the even integer. Okay, so what's the index of even integer inside Z? Because odd number and even number, right? So there are only two of them. partition your integer, correct or not? Your integer is partitioned into even and odd number. Okay, we phrase these facts inside the group theory term now, okay? And then multiply by the even integer indexed by the trivial subgroup again. Okay, so what is this? It is infinity again. 2z is infinite again. Okay. So infinity equals to 2 times infinity, so it's infinity. Yeah, so the really interesting part is when it is finite. Okay. Of course, there are a lot of infinity. Have you learned there are different infinity or not? Alpha, aleph, aleph, and then 2 to the power aleph, and then so on. 2 to the power 2, to the power 2, to the power 2. Keep going on. Yeah. And maybe you can try and discover what's this difference here. But z and 2z should have the same cardinality because you can enumerate the enumerable. Okay, or you form a bijection. Okay, so just now we start at the normal subgroup, telling us that coset is somehow abelian. Okay, so this is what we're gonna show now. So let's take a subgroup of G. Again, the followings are equivalent. Okay, the followings are equivalent. So there are 4 statements that are equivalent to each other. Okay, so first, suppose my subgroup is a normal subgroup. Okay, H is normal. Means what? For every element in H, okay, and every G in G, GHG inverse is in H. Okay, this is the definition. Please recall, if you cannot remember, here is it. Here it is. Okay, and then what does this imply? This implies that G applied on H and take G inverse is really equal to H. Okay, so this is the other definition I ask you to take. Okay, the first definition tells you what? If you have this element expression, right? This is equivalent to a set expression, which is GHG inverse is a subset of H. Okay, but really you can close it up. It's equal. Okay, H is the top. You can close it up. And then third statement, for every G, GH is equal to G, HG. Okay, this is what I told you just now. So you can somehow move this G inverse across. Okay, and the sets are equal. So note that these are equality of set. Okay, not element. So you need to check for all elements in H. Okay, this is how you check for the set. And then the fourth one is every left coset of H in G is a right coset. Do you think I'm repeating 3 and 4? No? Am I repeating 3 and 4 here? Think about it. Am I repeating 3 and 4 here? No? Think about it. Any difference between 3 and 4? GH equals to HG. So the left coset GH for all the G in G, all the left coset GH is equal to the right coset HG. And then the fourth line said every left coset of H is a right coset. Am I repeating what am I doing here? Is this too redundant? No. Let me here. I think any difference between these two lines? Yes or no? Is it redundant? Huh? Any idea? Is 4 repeating what 3 is saying or not? Huh? What's the meaning of? Oh, TFAE. So this is the following are equivalent. Any okay, the following are equivalent. Yeah. Any idea thingy? 3 and 4 the same? Yeah, good. Any idea? Don't know. Why want to say something? Are these two the same?
Maybe the element pick is still the same.
Yes, correct. So it just says that every left coset is a right coset. It doesn't say which right coset it is. Okay. Maybe GH equal to H Z. Right. Equal to some right coset. Not necessarily HG. Okay, this is what the fourth line tells you. Okay. Every left coset of H in G is a right coset. Any right coset, not necessarily coming from GH, HG. Okay. Does it make sense? Make sense, huh? Make sense or not? A question? Okay. So, but they are all equivalents. Okay. I let you try and prove. So let's see what I prepare here. You see what I prepare here? I let you try. Let's see what I write here. So we will do 1 to 2, 2 to 3, 3 to 4, and then equivalence between them. 1 if and only if 2, 2 if only if 3, 3 if and only if 4. Okay. And then I wrote down 2 to 1 is obvious, 2 to 3 is clear, 2 to 3 to 2 is similar, 3 to 4 is trivial. Okay, I let you try 5 minutes. Okay, see if you can do these trivial things or not. Try. Discuss with your friend. Prove the TSAE statement. Discuss with your friend. Yeah, the following are equivalent. Try and prove. I give you 5 minutes. So these are really like 30-second proof only for all of them. This is similar to how we prove the when phi x equals to phi y, and then the two left coset are the same and so on. It's really similar. Just apply definition. Okay, try and think about it, how to prove. I give you 5 minutes. You can discuss with your friend. Okay. I think the hardest one is the 4 to 3. The hardest one is 4 to 3. You don't know they are equal, but somehow you need to show that actually you go back to the same right concept. I mean, same meaning use the same G to B. That's the hardest one. So this exercise is testing your definition. You can make some noise if you want. If you see this one in the textbook, you'll cry a lot. It's obvious. It's trivial. Omitted. Okay, yeah, give you another 1 minute. Write it down for your level. Please try and write it down first. Make sure you know what you are talking about. A very good practice, even until now, if you are working. Okay. Okay. So, okay or not? Can we discuss together? So let's use some word to discuss, and then if you don't understand, maybe we can write it out. But in the real lecture notes, I'll write it out. Okay. So how to go from 1 to 2? You know that for OG, GHG inverse is a subset of H. Use H is a subset of GVG inverse. Okay. What have I wrote here? Since it is true for all G, such that GHG inverse is in H, you can take G to be G inverse, so that G inverse H, G is in H. But what does this mean? This means that we can conjugate by G on both sides. G inverse H, G inverse. Okay, where you get H back. Okay. So let me write down what I mean here. Okay, so I think I should write down. Okay. So we just take G to be G inverse. Okay, then we will have that G inverse H G is in H. Okay. But I claim that what? I claim that this implies that H is actually in G H G inverse. Okay. Why is this true? Because if G H G inverse equal to H, that means G inverse H equals G inverse H G equals to H1, for example. Okay, in H. Then you can conjugate on both sides, which you get G H1 G inverse, which is in the set of G H G. Okay, okay. So so what do I mean? So this operation here generally works for this subset inclusion. Okay, so you can see that G inverse HG is a subset of G. If then H is a subset of GHG inverse. Okay, yeah, this is the whole argument here. Okay, okay or not? So you show the red part here by checking on elements. Okay. Yeah, so the operation will go forward in subset inclusion. Okay, go forward. So you can move things from the left to the right. Follow these subset inclusion. Okay or not? Okay, so this is 1 to 2. Okay, because to get 2, we just really need to check. We need to check that H is a subset of G H G inverse. Okay. The other inclusion is given by 1 already. Okay. Only check H is a subset of G H G inverse. Okay. How about 2 to 1? 2 to 1 is obvious. Why? Because 2 is stronger than 1. Is it 2 is stronger than 1, right? Because 1 is just 1 inclusion, but 2 have 2 inclusion. Okay. Yeah, 2 is stronger than 1. So 1 is implied by 2. Everyone got it? Okay, do you get what I say? Yes or no? I'll repeat again. Okay. So I say 2 implies 1. Okay. If I have 2, then I will get 1. 2 is stronger than 1 because 2 have 2 subset inclusion. Okay. GHG inverse is a subset of H. H is also a subset of GHG inverse. But 1 only have 1 inclusion. So more than enough if you assume 2. Can get it or not, Jimmy? Okay. Okay. Yeah. 3. How about 3? So 2 to 3 is clear. Is 2 to 3 clear now? Clear, right? Okay, it's what I did just now. Okay, it's what I did just now. If you write G little HG inverse as sum H, then you can move G across. Okay. And then the other direction is the same. Okay, you multiply G inverse. 2 to 3 is clear. 3 to 2 is similar. Yeah, you also play the same trick. I'll try and work it out. I will post the proof as well. Okay, try and work it out and then compare with my proof. Check equality on set. You need to check on element. Okay. So the good thing about this subset equality is you can shuffle the H. You can shuffle the H. Okay. For example, GH1 might not be equal to H1G, but it equals to H2G. GH1 equals to H2G, but that's enough because you just need to be true inside set. Okay, you can shuffle around GH and HG. Okay, you doesn't need to necessarily equal on the element. Okay, on the nodes. Not necessarily GH1 equals to H1G, but GH1 equals to H2G is enough to show the equality of set because you just care about whether it's in the set or not. Okay, make sense? Okay, so that's why we only can show up to this step here. We only care about equality on set. Okay, 2 to 3, 3 to... Okay, 3 to 4. Why 3 to 4 is trivial? 3 to 4 is trivial. Is it trivial? Yeah, 3 to 4 is trivial. Why is it trivial? You already know that all the left coset GH is equal to right coset HG. So does it imply that every left coset in H is a right coset? Of course, right? Because you already write your left coset in terms of right coset. Right or not? So there's some logic here, some word you need to get around here. Okay, I already write my left coset to be left coset. Okay, then surely all these left coset we can write as right coset, which is a right coset in G. Okay, and then how about the other direction? I said that the other direction is other. And suppose every left coset in H in G is a right coset. Okay, how do you know that the right coset have to get from HG? For example, let's say your left coset is GH. Okay, how do you know that the right coset that the statement gives you is definitely HG? How do you know? Okay, so this is the question you need to address. GH can go to other H, HB, HC, HA, HD. Why is it necessarily HG? Okay, why? Show 4 to 3. Okay, so the idea is G is the common element in that set. Okay, G is the common element in the set. Okay, but why? Yeah, hash contain identity. So in particular, it contains G and G times identity, right? E times G. Okay. So these two are common. Okay. And then left coset partition your set. Right coset also partition your set. Okay. Okay, I mean the key point here is the common element here. Okay, you need to use the fact that there's a common element in GH and HG. Okay, and then how you deduce it? Yeah, how you deduce it? Try to think about it. Okay, yeah, how does the common elements will help you to find it? Okay, GH and HG. Okay. Okay. If you have G inside, if you have G inside your, so let's say if you have G inside your HG, you have G inside your GH. Okay. Why all the other elements have to agree? Okay. Why the left coset of HG is the right coset? Yeah, think about it. What time is it? 10:46. Okay. Let's go to another one. Okay. So try think about this, right? Think about again. Think about 4 to 3 again. Okay. How the common element G in GH and HG gives GH equals to HG. Okay, think about it. Cannot see. Okay, let me move the sky. Okay, yeah, how the common element G in GH and HG help you to show that GH equals to HG. Okay, try and think about it. Maybe we can come back next lecture. Okay. So I want to give you another last statement here. So proposition here. Okay, so if you have a subgroup, okay, and then you take a G, okay, take a G in your G, then a GHG inverse is always a subgroup in G. Okay. This one I think I briefly shown you when I introduced GA G inverse. So how to show subgroup? Identity is in there or not? Okay, is identity in there or not? GHG inverse. Yes, how? You just put GE G inverse. You will get the identity. Is inverse in there or not? Let's say H is invertible. Is GHG inverse invertible or not? Invertible, right? Because G also invertible. What else? Identity, invertibility. That's all right. Subgroup. What else? That's another one. Oh, closure. Yeah, closure. So if I G H1 G inverse multiplied by G H2 G inverse, is it in GH G inverse or not? Because H1 H2 is in the subgroup. Okay. Okay, this one is easy. How about the other one? Let's say your group has only one order. Okay, let's say order R. R is not important. So only, but the important is it is finite. Order R, then that group is normal. Okay, if you only have one subgroup of order R, then this group is normal. Okay. Why? Why? Anyone can quickly think about it? No. So it's a proper subgroup. Okay, so this has to be a proper subgroup. Okay, if there's only one proper subgroup. Okay.
Subgroup, the trivial subgroup.
No, proper. Usually we don't say trivial subgroup as a proper subgroup. Yeah. Usually we call trivial subgroup a trivial subgroup. Because usually we don't like trivial subgroup because it's trivial. Every group have this trivial subgroup. But it by definition is proper, but usually usually when we talk about proper, we mean non-trivial proper. No.
So this is non-trivial.
Yeah, non-trivial proper. If you like. Order of a group. R is a number. R is a number. Number in N. R is a number. Order R. Okay, why is it normal? Okay, how about you think about it and then we come back. The first exercise we do on Thursday is this one. Yeah. Center? No. Center is stronger than normal. Center is stronger than normal. Sorry? The conjugate of H is order, R order. Yeah. Yes, correct. Yes. Okay. You want to tell them? You say out loud. You say out loud. No, you say out loud. Just now when you talk to me, you say it out.
The conjugate of H.
So the conjugate of H is also order R. But conjugate of H is also a subgroup by A. So meaning these two groups have to be the same because there's only one order R subgroup. So meaning H equals to GHG inverse. But just now we show that those are equivalent statements where H is normal. Okay. Okay, how about so Thursday we come back on 4 to 3. Okay, 4 to 3. Okay, we show 4 to 3 in the first exercise on Thursday. Okay, see you on Thursday.
Okay. That is also